Okay, let's get into the second part of the tutorial. Here is the agenda for the next 1.5 hours. We will look at the routing protocols in IPv6 at a high level. And as I mentioned earlier, this is designed to be a primer, and we would not be getting into a lot of details of each of these protocols listed. It could take hours, as you know. And we also will cover a couple of tunneling technologies, followed by the routing in IPv6. Then eventually we'll get into DOCSIS implementation aspects of IPv6. Like IPv4, we have two types of routing protocols available in IPv6. Exterior gateway routing protocols and interior gateway routing protocols. For EGP, obviously there is just one protocol out there, which is multi-protocol BGP. And for IGP, we have RIP Next Gen. Integrated ISIS support has been enhanced for IPv6 as well. And then we have OSPF v3. Keep in mind, OSPF v3 doesn't support IPv4. It is not like backward compatible version or anything like that. So we have OSPF v2 for IPv4, and OSPF v3 exclusively addresses IPv6. Let's take a high-level look at RIP's Next Gen. We do know that RIP is a distance vector routing protocol, and as far as versions IPv6 support for RIP is concerned, a lot of the characteristics of the RIP has been retained. RIP-NG also is a distance vector routing protocol. It has got the hop limit of 15. It employs split horizon, Poisson reverse, and all kinds of stuff, whatever is out there. Older version of the RIP. And it uses multicast, like RIP v2, because we had RIP version 1, which was using broadcast, right? V2 had v4 multicast. So RIP-NG uses IPv6 multicast, and it uses UDP, the port number being 521. There are updated features for IPv6, and as you can see here, there is a side-by-side comparison between the RIP version 2 packet header format and RIP-NG packet header format. And obviously what is carried in the route table entry, because the routing update message would have multiple route table entries, right? So what is carried in the route table entry is the IPv6 prefix and the prefix length. And of course, like RIP version 2 for v4, we have a route tag which we can carry to identify the routes. But if you are not using the route tag, the field will be using just 0, and the metric is similar to RIP version 2, which is hop count. One thing to keep in mind, I don't know you have noticed, the next hop is missing. And we do know that in RIP version 2, the use of next hop is if a router is advertising some of the routes for which he wants to mention a next hop other than himself, then he can insert that next hop field with the route table entries. Here, the next hop option with RIP support for IP version 6 is not omitted. Rather, the way it is implemented is it makes use of the route table entry, this prefix, route tag, prefix length, and metric format, but it has defined a metric of FF. And if there is a route table entry with a metric of FF, what that says is it is actually carrying the next hop address, not a destination route itself. And also the route tag and prefix length would be 0 in that case. So any route following that next hop would be the actual route updates corresponding to the next hop. So that is how the next hop is handled in RIP-NG. Moving on to OSPF v3. These are some of the key differences between OSPF v3 and OSPF v2. We do know that in the IPv4 world with OSPF v2, the protocol processing is done on a per subnet basis. If you have multiple subnets configured on a link, right, whether it is a direct connected link between two routers or a multi-access network, then you can have adjacencies formed separately or corresponding to each subnet. However, in the case of OSPF v3, the processing is done on a per link basis. And we do know that in IPv6 world, the nodes could be having multiple IPv6 addresses assigned to an interface. And if there are two directly connected interfaces corresponding to two different nodes sharing the same link, even if those two IPv6 addresses are not part of the same subnet, they can communicate with each other. So because of these things, the processing of OSPF in v3 is done on a per link basis and not on per subnet. A new flooding scope has been added, which is for the local link called link local specific flooding, in addition to the area level and the autonomous system level flooding scopes. And explicit support for multiple instances per link. Because if you know the way OSPF v2 works is, once you add one of the interfaces into the OSPF process, right, so the corresponding area is also assigned and it automatically inherits the instance. So you cannot have multiple instances of OSPF running on a link in the case of OSPF v2. But OSPF v3 allows you to have separate instances of OSPF running on the same link if you configure it that way. And it could be applicable where you want to have two instances running on the same link corresponding to two different autonomous systems, for example, or two different areas sharing the same link. And in such scenarios, you can have separate instances per link. And OSPF uses IPv6 link local addresses, multicast and unicast addresses in the hello messages and other OSPF messages. And another key change is the authentication method. We know that OSPF version 2 support authentication, but because of the fact that in IPv6 we have authentication support by means of using the extension headers for IPsec, the authentication header and encapsulation security payload headers. So you don't need to have additional authentication support at the OSPF level. So what you could do is, if you decide to have authentication, then you can make use of the IPv6 level authentication. So there is no authentication defined in the OSPF, and you cannot configure anything around that. And another thing is handling of unknown LSA types. In OSPF v2 implementation, if the router doesn't understand the LSA, it will simply discard it. But with v3, if it doesn't understand the LSA, it can be configured to flood it to the rest of the network, because that could be helpful sometimes when some new LSA is introduced, right, as the protocol evolves, and the network is going through some transition phase, and some of the routers can understand and process it and some cannot. Now, we talked about the differences in the previous slide. Let us take a look at the similarities between v3 and v2. As far as the packet types are concerned, they are pretty much retained. We still have the hello packets for the adjacency formation. We have the database description packets, again part of the adjacency formation, then link state request and update packets, and also link state acknowledgement packet. And interface types, similar to v2 world, we have point-to-point, point-to-multipoint, broadcast, non-broadcast multi-access, and even it supports virtual interfaces. And also it has the concept of LSA flooding and LSA aging. Here is a high-level comparison of OSPF v3 and v2 headers. As you can see, the authentication type field and the additional authentication information has been taken out, because what you see on the left side is an OSPF v2 header, and what is on the right side is the OSPF v3 header. And an instance ID has been added, right, so that you can run multiple instances of the protocol. And As far as router ID and area IDs goes, they are still using 32-bit numbering space. So if you don't have any IPv4 addresses explicitly configured, then you would have to explicitly assign a 32-bit router ID. So the router ID and area IDs still use 32-bit numbers. Any questions before we move on? Moving on to enhancements in BGP to support IPv6. We do know that BGP has had this multi-protocol BGP for IPv4 support out there for quite some time to allow the multicast over BGP and MPLS VPN over BGP and things like that. So the same is made use of the multi-protocol extensions for the BGP is made use of to support IPv6 as well. So there is no separate BGP protocol defined for IPv6. So we already have the multi-protocol extensions out there for BGP4 to support different protocols. So there are additional definitions made in terms of attributes and TLB values and stuff like that to support IPv6 as well. And the two key non-transitive attributes defined to support IPv6 are multi-protocol reachability, network layer reachability information, and unreachability NLRI. And there is an address format identifier which will identify it as corresponding to an IPv6 address. And to support IPv6 and exchange the IPv6 prefixes, the peering routers should advertise in the BGP capability about the support for IPv6 AFI as well. So these are the two key attributes, non-transitive attributes added to support IPv6, what I mentioned earlier. And looking into the details, it has an address family identifier defined for IPv6. AFI ID is 2. There is a corresponding RFC which talks about it in detail. And then there are sub-identifiers under that IPv6 AFI for unicast or multicast, or if it is using both unicast and multicast, etc. So as far as the neighbor establishment of the neighbor is concerned, so it still uses TCP, and again it's BGP4, it's not BGP6. It's only like multi-protocol extension support IPv6 as well. And the connection could be set up over IPv4 or IPv6. So you can use either the IPv4 source and destination address or IPv6 source and destination address for the connection establishment. And even if IPv4 is not configured, you will have to explicitly configure a router ID, and that still stays as 32-bit for BGP4. Any questions before we move forward? As far as IPv6 support for ISIS is concerned, the way it is implemented is new TLVs have been introduced to support IPv6 addresses. And that's the IPv6 reachability TLV to carry the IPv6 routes, and the second is the IPv6 interface address TLV used in the ISIS messages. And there is a network layer protocol ID defined for IPv6, as you see the number here, because ISIS is a protocol which supports multiple, it's a routing algorithm which supports multiple protocols, right? So OSI and IPv6 as well as IPv4. So there's a separate network layer protocol ID corresponding to each one. And that was what we talked about, was single topology ISIS, just by making use of the TLVs. And then in the single topology ISIS scenario, it would support, right, with separate network layer protocol IDs and the corresponding additional TLV values IPv4 and IPv6, but it would be a unified topology running across the network. But if you want to have separate topologies corresponding to separate protocols, like V4, V6, and multicast, then you can go with multi-topologies ISIS extensions. There are RFCs defined to support that. And if you have that configured, what happens is when the adjacencies are formed, there would be a separate multi-topology adjacency maintained corresponding to each of the topologies. So not every router will be participating in a network. Not every router will necessarily be participating in all the different protocols. So I think if you look at this example here, this is a multi-topology ISIS implementation scenario. The routers identified as blue supports IPv4 and IPv6, but the ones identified as yellow are only IPv4 enabled router. So in the yellow ones, you don't have to run V6. If it was a single topology, because it was like a uniform topology, every single one would be running V6 and V4. Any questions so far? Because like I said, the intention for the routing section was not to get into all the details, but rather have a high-level look at the key differences compared to the V4 versions of the protocol out there. And getting into tunneling, as you know, the tunneling is a transition technique. So when the IPv6 deployment is evolving, it is possible that there will be some networks out there with islands of IPv6 networks with IPv4 in between. So sometimes you have to have some mechanism to interconnect, right, through those IPv4 networks. So there are two ways to do it. One is manual configuration. So you could be having at the border, right, between the V6 network and V4 network, the routers explicitly configured to tunnel the V4 traffic over V6 traffic over V4 to the other side of the tunnel, right, over an IPv4 network, so that you will interconnect to discontiguous IPv6 networks. Manual tunnels are typically not going to scale. Another way to do it would be automatic tunneling of IPv6 over IPv4, and there are multiple ways to do automatic tunneling. In the case of automatic tunneling, you don't have to manually configure the tunnels. And manual tunnels, as you know, are point-to-point tunnels. So there is an origination point and a destination point typically, right? But automatic tunnels doesn't have to be configured manually, and it is point-to-multi-point tunnels. And there are a couple of automatic tunnels. We'll take a look at it, the implementation, which explains it a little more in detail. 6-to-4 is one of the automatic tunnel methods. And the way 6-to-4 works is, IANA has assigned 2002 :/16 for 6-to-4 tunneling. And in order for making it automatic and may allow V6 to find out the corresponding V4 address and create a tunnel and carry it over to the other side, the IPv4 address of the destination or the node is embedded in the network portion, prefix portion of the address. So it is 2002 plus 32-bit IPv4 address. And unlike the manual tunnels, as I mentioned earlier, 6-to-4 tunnels are not point-to-point. They are point-to-multi-point address. And the key here is the V4 address is embedded. And when somebody gets a 6-to-4 address in 6-to-4 format, he can extract the V4 address from the V6, and that can be used to transport the V6 packets over a V4 network, so that it will receive the V4 address, whichever is destination address, right, and then from there it can be de-encapsulated and extracted. So maybe this gives a better explanation with the diagram here. We have two hosts, host A and host B, which are connected to two IPv6 networks with an IPv4 island in between, right? So there should be some kind of tunneling mechanism employed in order to get this working. And in this case, they have implemented 64 tunneling. And as we can see, the router should be 64 tunneling aware as well, because these are the routers which will do the V6 to encapsulation of V6 packets into V4. So let's go back and look at the address, right? So the 2002 is fixed. So looking at that, right, first 16 bits you can tell it is a 64 tunnel based IPv6 address format. Then you insert the 32-bit IP address here. That makes it 48 bits, right? After that you still have 16 bits available actually for subnet level addressing if you want to have multiple subnets on your IPv6 island over here. Then the rest of the 64 bits is the interface ID portion, which is not used for the tunneling. The tunneling, the key thing is the embedded public IPv4 address. So let us look at this scenario here. If IPv6 host A wants to communicate with IPv6 host B, through some mechanisms it is aware of the address of IPv6 host B, right, which is 2002 column such and such, which is a /48 prefix it is using. And as you can see, there is a corresponding IP address, right, which is assigned to the remote site 64 router. And what host A would do is, if he wants to send a packet to host B, like any other IPv6 packet, it will send with the destination address, which is specified here, which is a 64 address. After the 64 router on the local side, closer to host A, right, which is the border router interconnecting V6 to the V4 network, receives the packet, it can look at the destination address, and because of the 2002 prefix, it will identify that it is a 64, right, address, and then it will look into the next 32 bits to extract the destination IPv4 address. After doing that, so it has an IPv4 address it can use to encapsulate the original IPv6 packet and route it through the IPv4 network. And that IPv4 address was configured on the remote 64 router. Remote 64 router, right, which is again configured for 64 tunneling, upon receiving that address, will de-encapsulate and then forward that IPv6 packet to host B. That's how it is going to work. Any questions? It's pretty straightforward because instead of manually configuring the tunneling, you can, the IP address for the destination termination point of the tunnel is embedded in the V6 address. I mean the IPv4 address is embedded in the prefix portion of the V6 address, which makes it automatic for the router to do the tunneling. This is the same thing we explained in the last slide. Source host A wants to send a packet to destination D, and then the intermediate router picks up the IPv6 address, extracts the destination IPv4, encapsulates that, as you can see, right, IPv4 header, then IPv6 header, and then IPv6 data, and then forward it through the IPv4 island. It receives the remote site 64 router, and then it will extract the IPv6 packet from the IPv4 packet and forwards it to the remote site IPv6 network, which will be eventually received by the host B, which is the destination node. And automatic 64 relay routers are required when these islands of IPv6 networks which are using 64 tunneling and the corresponding addressing mechanism needs to reach the global V6 internet. A 64 relay router typically would have an anycast address configured and announces that to the rest of the routers. And the way these 64 island networks can reach the rest of the internet is by using the 64 relay router. It's the gateway to the rest of the IPv6 internet. Any questions on 64? We have one more tunnel we we are covering the like the ISATAP, inter-site automatic tunnel addressing protocol. Somewhat similar in this case also, an IPv4 address is embedded in an IPv6 address. But the difference is, in the case of 64 tunnel, the v4 address was embedded in the prefix portion or the network portion of the IPv6 address. But with ISATAP, the v4 address actually is part of the host portion or the interface identifier. So when it creates the interface identifier, it makes use of the 32-bit IPv4 address to construct the full 128-bit IPv6 address. And routers are involved in this also to get the tunnel working. We will see that in one of the subsequent slides. And this is the syntax for the IPv6 address for supporting ISATAP. 64-bit unicast prefix can be any prefix, a valid prefix assigned to the a provider or enterprise. And if you look at the 32-bit side, I mean the host identifier side or interface identifier side, the first 32 bits are constants. The 5EFE represents the OUI for INA, and preceding that we have all zeros, and depending upon whether it is a private address or public address, we will specify it as a 1 or a 0 actually in the preceding bits prior to the 5EFE. But the first 32 bits of the interface identifier portion identifies that this address is an ISATAP address, and the IPv4 address is embedded right in the interface identifier portion as the last 32 bits of the interface identifier. The way the tunneling works is, first of all, the router connected to the link, one or more routers connected to the link should be configured for ISATAP tunneling. When the router sends out the router advertisement, right, it typically sends out multiple prefixes, and one of the prefixes would be designated as a prefix for ISATAP tunneling. Once the router advertisement is received by ISATAP host specifying the ISATAP prefix, the host can create the interface identifier portion by embedding the 32-bit IP address plus the well-known piece of the other 32-bit. So when an ISATAP host wants to send IPv6 packet, so all what it has to do is to, as long as it knows the destination address, it just needs to extract the IPv4 address from the ISATAP v6 address and then encapsulate the v6 address into the v4 packet and just forward it. Any more questions before we move on to the DOCSIS implementation of IPv6? Are we good? For the folks who are familiar with the cable and DOCSIS world, the IPv6 addressing support for cable modem management, all the devices which gets connected to the CMTSs, as well as the CPEs, the subscriber side devices, was introduced in DOCSIS 3.0, the latest set of specifications which came from Cable Labs. And this is a reference architecture. What you see here is on the cable provider side, you have the MSO, multiple services operators admin domain, right? And at the edge, you have the cable modem termination system, which is interconnecting your cable plant side, typical HFC, hybrid fiber coaxial plant side, with the rest of the provider's network. And you do have the back office servers and provisioning systems for the initialization, provisioning, and management of the cable modems, as well as the address assignment functions for the CPEs and modems. In the IPv6 world, for the DOCSIS, we have three kinds of access models available. In access model 1, the CPEs are directly connected to the cable modem and gets assigned a single IPv6 address. In the access model 2, as you can see, there is a home router, even though the home router in this scenario is a standalone router sitting behind the cable modem. There is a home router and there is a home network or a small business network behind the home router. So there could be multiple interfaces supporting multiple subnets, right, by the CPE router. And in access model 3 as well, you have a home router. The difference is the home router is embedded in the cable modem itself. Instead of having two different devices sitting at the customer premises side, there's a single device performing the cable modem functionality, log on to the provider's network and gain access, right, and as well as act as a modem router for the local network. And management prefix, what you see here is the prefix used for assigning IP addresses to the cable modem. As you know, even though cable modems typically acts as bridges, cable modems needs to be assigned with an IP address for the management purposes, for the initialization and subsequent maintenance. And in the V4 world, we provide an IPv4 address to the cable modem, and in the V6 world, we can provide an IPv6 address. One thing to keep in mind is this management address doesn't have to be a globally routable address, because the management domain is confined to the particular provider's network. So he can even go ahead and use the unique local addresses for the purpose of doing IPv6 addressing for the cable modems, because they don't have to communicate to the rest of the internet. It is basically for the management purposes. And looking at the service prefix, for access model 1, the prefix length would be typically 64, but for the access models 2 and 3, it may make sense to provide a 48-bit prefix. That's where the prefix delegation also will come into picture, because the CPE router, right, can request for a prefix instead of a single IP address from the DHCP server, and once it receives this prefix, what it can do is it can assign separate subnets to the interfaces of the router corresponding to different links, and then it can implement stateless address auto configuration so that the CPEs behind the CPE router would get the addresses automatically created instead having to access the DHCP server. And the prefix delegation can be employed in access model 3 as well, because you have an embedded router and multiple subnets behind that. And this is just a little more details on the customer premises side. What would you have if you have a router implemented on the CPE side? And nowadays, this is very typical even for residences, right? Multiple systems like laptops and even mobile devices, and some wired connections. Combination of wired and wireless connections are very common out there. So it is in this model, if the router is receiving a prefix /48, for example, then it can makes use of the 16 bits of subnet level address to create multiple prefixes corresponding to each link and incorporate auto discovery, auto configuration to assign address, IPv6 address to all these CPE devices. Let's take a high-level look at V6 features in DOCSIS 3.0. It introduces the concept called the lightweight router function, which is the embedded router in the cable modem itself, which we kind of covered already. That's where the prefix delegation also come into play. And cable modem can be managed by using IPv6. However, you have different permutations and combinations of the scenarios available. Some providers may want to manage the cable modems using IPv4 address but provide V6 addresses to the CPEs behind the cable modem, and that option also is possible. And if the network is transitioning from V4 to V6, it is quite possible that you may have a mix of back office system, right, the provisioning and other management systems, some of them supporting only IPv4, some of them supporting V6 and a combination. So in that case, cable modems can be configured in dual stack mode with V6 IP address as well as V4 IP address. If it is configured for dual stack mode, it will pick up two addresses, one IPv6 and one IPv4 address. And if you have a mixed environment during the transitioning phase, then the modem can be managed either by using a V4 address or a V6 address. And the same option is available with DOCSIS 3.0 for CPEs as well. You can assign either a V6 only address or a dual stack V6 and V4 address to the CPE devices. Now getting into the theory of operations. CMs can operate in either bridging or routing mode. Typically the cable modems would be in bridging mode, but it is possible that modem is in bridging mode, but there is an embedded router in the modem instead of having a standalone router sitting behind the modem. And as far as the management stack, that is CM management IP stack is concerned, it has three different modes available: IPv4 only mode, IPv6 only mode, or dual stack mode. And dual stack mode will be helpful, as I mentioned, during the transition phase, right? And what IP level initialization the cable modem will go through, whether it will do IPv4 or IPv6, that is commanded by the CMTS. CMTS is the head-end router, right? Cable modem termination system is the aggregator to which all the cable modems get connected via your cable network. And the CMTS has control over telling the cable modem whether he wants the cable modem to use IPv4 based initialization or IPv6 based initialization or the combination. And it does by sending a MAC management message. It is a control message which is sent out by the CMTS towards the cable modem, which is more like a broadcast. Everybody will get to see it. It's called a MAC domain description message. And in the absence of that particular message, the cable modem assumes that V6 is not supported and it will try to do the V4 based initialization, the older version. As far as the cable modem provisioning is concerned, it is the process of initialization of the modem and establish the connectivity, the CMTS, so that it can start using the services. So it has the layer 2 provisioning, and then the next step is it will acquire the connectivity. If it is configured to use IPv6, it will acquire the IPv6, and then for folks who are familiar with the DOCSIS, there is another phase during the initialization at which time it will contact a time of day server and collect the time of day information, which will be used in the log messages from the cable modem. And this configuration file, what is mentioned here is a DOCSIS configuration file with parameters which provides restrictions and capabilities from the access and the service perspective, what modem can, at what speed modem can send on certain flows and things like that. Basically the implementation of QoS, number of CPE addresses supported, and all those things can be done through the configuration file. It basically, every time the modem initializes, it sends down that DOCSIS file with certain settings which is decided by the MSO. As far as layer 2 provisioning goes, as I mentioned, the MAC domain description message is what tells the cable modem that it has to, what kind of IP initialization mode it has to go for, whether it is IPv4 or IPv6 or dual stack. And there is one more provisioning mode called alternate provisioning mode. The way the alternate provisioning mode works is, It will try to acquire an IPv6 address, and if it fails to acquire IPv6 address, then it will fall back to an IPv4 initialization mode. That is what is called alternate provisioning mode. One thing to keep in mind is the cable service providers are not going to support stateless auto configuration for assigning addresses to the cable modems, except for the case where you have the prefix delegation and the CPE router doing stateless address auto configuration, which is different. The only stateful address configuration is supported for providing the cable modem management addresses, so that the provider can explicitly track the cable modems with the IP addresses. So the router advertisement message, which is supposed to be sent out periodically by the CMTS or in response to a router solicitation message, will need to have the M and O bits set appropriately. If you recall our DHCP-V6 section, M tells the nodes, right, depending upon the setting, whether the configuration IPv6 address acquisition happens through DHCP-V6 or auto configuration. And O is the other configuration information, which is if you do the stateless address auto configuration, how would you collect the other configuration information, such as the list of name servers, domain name, etc. So M and O bit are actually set in such a way that stateful DHCP-V6 is what will be done by the cable modem to acquire an IPv6 address, because the bottom line is MSOs want to have full knowledge of which IP address is assigned to what modem. Here is a sample flow of full cable modem provisioning. Any IP node, after it goes through the initialization, the very first thing it is going to do is a link local address assignment. It has to assign a link local address because there is this well-known prefix for the link local addresses, right? And it can use that along with the EUI64 format, making use of the MAC address to construct a link local IPv6 address, which will be required for the rest of the neighbor discovery and other link layer control messages. After it creates the link local address assignment, it sends a neighbor solicitation message for duplicate address detection, which actually gets hit, will be received by the CMTS. And for that request, obviously, it is not going to expect a response until there is a MAC address conflict itself somewhere, which would be a denial of service or theft of service scenario. But typically, you wouldn't expect a response for that because the link local address was created by making use of the MAC address, which is expected to be unique. As I said, router advertisement messages are sent periodically, but during the initialization time, the cable modem doesn't have to wait for the next router advertisement message to come in. It can send a router discovery, router solicitation message, and then it will receive the router advertisement. And it will have the M and O bit set properly, so that what it has to do is DHCP-V6 to acquire an IP address. So the very first message sends out for DHCP transaction is solicit. I will talk about this rapid commit option later. So DHCP solicit goes and it gets received by the CMTS. What the CMTS does is CMTS encapsulates the solicit message, which is nothing but similar to the DHCP discover in the V4 world, in a relay forwarder message, after adding some of the options which CMTS wants to add, right? And relay forwarder message is forwarded to the DHCP server. DHCP server, if this modem has been configured already and provisioned in the back office systems, the DHCP server is going to provide a relay reply message. Relay reply message will have an encapsulated advertise coming in from the DHCP server side. That is more like an offer, right, in the V4 world. So relay reply message is received by the CMTS. CMTS extracts the advertise message and forwards back to the modem. And if modem lacks the IP address offered along with the other options, it is going to send a request. Request will have to be encapsulated in relay forwarded as well, and it comes back in relay reply with the reply that is confirming that advertise has mentioned about an IPv6 address. Request has requested for that IPv6 address from the DHCP server, and the reply has confirmed that that IPv6 address has been assigned to this modem. Now, you see here the rapid commit option. With the rapid commit option, what happens is the advertise and request are skipped. So when a cable modem sends a solicit, which is a DHCP discover message, like with rapid commit option set, and is received by the DHCP, DHCP server can send the reply back with the IPv6 address by skipping the intermediate phases. So it makes it much faster as far as the processing is concerned, because two packets are skipped at the cable modem side, at the CMTS side, as well as the DHCP server side. But what is the flip side? There is no way to explicitly track whether that cable modem has actually decided to use the IPv6 address or not, because it is possible that cable modem has requested IPv6 address using rapid commit. Two different DHCP servers may have provided the address, and there is no way to find, and it can't result in inefficient utilization of the available address space. But it makes the process faster, but I don't think it will be a recommended option to use in provider managed IP addressing scenarios. After receiving the global IPv6 address, not necessarily global, any address, right, even the unique local, which is used for the cable modem management purposes, another neighbor solicitation message is sent by the modem to check and verify whether there is an address duplication anywhere, which is not expected to receive any response back. And as you see, if you incorporate rapid commit, advertise and request messages are not required, but that has got some drawbacks as well in doing so. Now, moving on to the rest of the provisioning process. As I mentioned, during the initialization time, cable modem needs to contact a time of day server and acquire the time of day information, which will include the time of day information in the log messages generated by the modem later on during the maintenance time. And that request is made using IPv6, and then it gets the response back. And the next is the docsys file I was talking about with the configuration parameters. So typically cable modems use TFTP to contact the TFTP server and download the docsys file. So that also would be using IPv6, and it receives the TFTP response, the configuration file. And if all is good, it is going to send a registration request to the CMTS, and it comes online using an IPv6 address. And if it is configured for dual stack, after this stage, it can try to acquire a v4 address as well. Any questions? I think we kind of talked about dual stack management already. Whether the cable modem needs to go with dual stack management is decided by the CMTS, and it will mention in the MAC domain description message by specific settings in the MDD message, which goes out periodically from the CMTS. So first of all, it will register in either IPv6 or IPv4 mode. After completing the registration, then it can try to acquire the other version address. Typically useful during the transition periods, as I mentioned. Alternate provisioning mode, again we covered, you can specify which is the primary provisioning option, like whether you want to use IPv6 or IPv4 as the primary mode, and if it fails, then it will back up to the other one. If typically V6 would be the primary mode in networks transitioning into V6, right? And if it fails due to some reason, then it will fall back to V4 and then complete the registration. Now CMTS and CM requirements for IPv6. CMTS can be a bridge or a router, but typical implementations out there are CMTS acting as a router. And it needs to be a relay agent for DHCP v6 messages, because that is the one which sends out the DHCP relay forwarder message, which encapsulates the original messages coming in from the client side, and the DHCP relay response message will be de-encapsulated to extract the original client message and send it back to the client. And it has to participate in neighbor discovery messages. So it sends the router advertisement messages, it processes the router solicitation messages, and if it receives a router solicitation message, it will send out an out-of-cycle router advertisement message right away. And also it participates in the neighbor discovery in such a way that it can either act as a proxy, or it is supposed to forward the neighbor discovery message from neighbor A on the cable side to neighbor B on the cable side, if A and B wants to communicate to each other. And CMTS is supposed to support the multicast for IPv6 as well, ASM and SSM, and the forwarding of IPv6 control traffic. IPv6 control traffic is nothing but the MLD V1 and V2 messages, depending upon the implementation, which is typically, which makes use of ICMPv6. And backward compatibility should be out there for cable modems running previous versions of the DOCSIS, because IPv6 support was introduced by DOCSIS 3.0, but in the field there could be more modems running DOCSIS 2.0, which doesn't support V6 or DOCSIS 1.1. Then CMTS should support backward compatibility and let it come online using an IPv4 address, and support V4 multicast as well. As far as CM side requirements are concerned, the address assignment itself happens through DHCP v6 for cable modems, as we mentioned earlier. It supports alternate provisioning mode and dual stack mode. With management of the CM can be done through SNMP. SNMP management can be done through IPv4 or IPv6. And if it is dual stack, some of the systems might be using V4 and some other systems might be using V6 for the management purposes. And regardless of whether the cable modem has been configured with an IPv6 address or an IPv4 address, the CPs behind the modems can be assigned with a V6 address or a V4 address. As long as the cable modem is a DOCSIS 3.0 capable cable modem, it is supposed to transparently forward V6 as well as V4 packets towards the CMTS. In the case of a cable modem which has got embedded or built-in router functionality, it has to implement DHCP v6 client for the purpose of acquiring IPv6 prefix, right? It will request for a prefix delegation by specifying that particular option while sending the DHCP solicit message. But keep in mind, prior to that, the cable modem might have already acquired another management address, because this prefix is being requested by the embedded router so that it can assign additional subnets, right, for the links connected to that router on the CPE side. And obviously the router needs to support serverless address auto configuration for the CPE host, and it should support prefix delegation as I mentioned multiple times earlier. And on the CPE side, the address assignment would be based upon the slack. And as far as the CPE router is concerned, it is supposed to support router solicitation, router advertisement, neighbor solicitation, and neighbor advertisement as well, because it is as good as any other router sitting on a link. So it has to perform all the neighbor discovery functionalities. And the configuration information such as the list of name servers and other data, it receives from the DHCP server and it propagates to the home CPE devices. So for that it can use the DHCP v6 itself, but the other configuration option for that. And it should support MLD version 1 and version 2 multicast listener discovery protocols on the CPE side too. Any more questions? So technical discussions pretty much ends here. These are some possible address assignment strategies in the cable world. The easiest way to implement IPv6 would be go with a dual stack strategy, where you will first of all enable your IP core with dual stack IPv6 as well as IPv4 addresses. Then you make sure that all your backend servers, right, the provisioning, the management, and everything, OSS systems are v6 compatible and also can be used, can be reached through IPv6 addresses. And then the next step would be for the cable modem management, turn on dual stack for the management. And for the CPE address assignment also, support dual stack for the CPEs. Provide a global IPv4 address and a global IPv6 address. In order to do that, the provider should have enough IPv4 addresses in hand to continue giving out the v4 addresses. But the advantage is this is the simplest scenario, because you don't have to have any kind of large scale or carrier grade NAT required in the network, because you are assigning a global IPv6 address and a global IPv4 address to the CPEs. So if the CPEs needs to communicate to the v4 part of the internet, it can use the global v4 address, and if it needs to communicate to the v6 part of the internet, it can use the global IPv6 address. However, most of the providers out there are running short of the v4 addresses, right? So in such cases, one option would be start offering only the IPv6 addresses, single stack IPv6 addresses to the CPEs on the customer premises side. The flip side is, we know that the internet is going to continue running on, major portion of the internet will continue running on v4 for quite some time, right? For the foreseeable, at least for a few more years. Then if a CPE which has been assigned with an IPv6 address needs to communicate either internally or into the internet to the v4 part of the world, and there should be some kind of network address translation happening at some place, right? So this has to be carried out at large scale or using carrier grade NAT. So 6-to-4 NAT mechanism will have to be in place for this to be implemented. Another option is go with dual stack, but assign a public IPv6 address and a private IPv4 address. Public IPv6 address can be used by the CPEs to access any global IPv6 destinations, right, including the v6 portion of the internet. But private v4 address can be used only for communications internal to the provider. But if it needs to reach to the global internet, then there will be an address translation required. Then you would have to go for NAT 4.4. Typically, it will become NAT 4.4.4 because there is already another level of NAT which happened at the customer premises side itself. Again, I haven't included, there are some other options also, like 6RD, another variation of 6 to 4, which some customers may consider during the transition phase for IPv6 deployment. So any more questions? So otherwise I can give you almost half an hour free time. Thank you so much for attending. Hope it was helpful.